Hello, welcome to a new chapter. Let's do the exercise 2 that says a charged particle moves in space with a constant magnetic field B such that the vector potential A is A equals 1/2 B cross R. If Vi and Pj are the Cartesian coordinates of the velocity and canonical momentum conjugate to xi, respectively, evaluate the Poisson brackets, blah blah blah. Okay. I think you haven't done the Poisson bracket yet, so let's define what a Poisson bracket is. This is the sum from I equals 1 to 3 of partial A with respect to xi times partial B with respect to pi minus partial B with respect to xi partial A with respect to pi. Before starting, let me calculate this important Poisson bracket xi pj because we will need it in this exercise. Let me put here k. We have partial xi with respect to xk, partial j with respect to pk minus the same thing but in reverse order. Pj and xi. This is 0 because p and x are independent variables and this is the same thing, so we can delete it, and this is just a Kroneker's delta ik and jk. So this delta cancels this sum and makes this k as a I. So this is ji or ij is the same. So we conclude that this important Poisson bracket is just this. Okay. So we start the exercise computing the Lagrangian, that is 1/2 mv squared minus the potential, and notice that I write u instead of v because we have here a charged particle, and then we need the concept of generalized potential that you already studied with Santi. So remember, the generalized potential for a charged particle moving with an electric or magnetic field is just the scalar potential minus q over c v dot a. But in this case, there is no scalar potential, so we only this term must be taken into account, so minus plus q over c v dot a. Let's calculate the conjugated momentum defined by the partial derivative of L with respect to v, and this is mv plus qca. Let's isolate v. That will be 1 over m p minus q over mc a. Okay. And if we are interested in vi vj, we will have 1 over m pi minus q over mcai, and the same thing but with a j here. Is also a nice property. If you have a plus b, c plus d, the Poisson brackets fulfill this property. This is equal to ac plus ad plus bc plus bd. But there is another important property which Santi will teach you today, I think, is that xi xj equals pi pj equals 0. Let me delete this because you already know. And another important property is that if you have a constant magnitude, alpha, times a function, then it's true that this is equal to alpha beta A, B. So the implication of this property here is that we can distribute this Poisson bracket. First of all, this with this, but Pi Pj is 0, so nothing to say here. And then we have 1 over m minus qmc minus qmc. So minus q m square c. Remember, we can factor out the constant terms in a Poisson bracket. Okay, and the thing that remains is Pi aj. We will write plus q over m square c Pj ai. So let's factor out this constant q over m square c. We will write in this way because I like it more. We then have to work it out a little bit. We are interested now in calculating PAB. I write A and B to obtain a general formula and then substitute A and B by JI or IJ. Okay, what is AB? A, the vector A is 1/2 V cross R in this exercise. So if we are interested in the the component B, then you know that the sum from C equals 1 to 3, sum D equals 1 to 3, epsilon V, this index, and CD. And you must write here V, C, and RD. But RD is better if we write XD, the D component of the position vector. But if we have repeated indices C and D and a sum, we can forget these sums because the Einstein's summation criterion, repeated indices implies a sum. So we can factor out this term here because all this is a constant magnetic field and the Levi-Civita symbol is also a constant. So we can factor out 1/2 epsilon BC D VC, and then the only thing we have left is PA, XD. But this is minus XD PA, and this is delta dA because of that. So we add a minus sign here and delta dA. So we can write instead of D here A and delete this. Let me write V blue. So using this calculation, we can now finish our previous calculation. Q over M square C times JI. So minus 1/2 epsilon JI. So A is J and B is I. Perfect. And now minus with minus is plus 1/2 epsilon, and I will invert J and I, B, C. But you probably know that if I invert two indices, then the sign changes. So this is the same as minus, let me see, IJC. And because of cyclic property of this symbol, this is equal to IJC also. So this minus with this minus cancels, then we substitute this quantity here, and it's the same as the other term. We cancel 1/2 and delete this, and that's it. This is the final result to the first Poisson bracket. Let me write K instead of C, it's nicer. Okay, let me put the Lagrangian here, and this is true, okay. And let me put V here and this here. So before continuing, let me tell you a nice property. Suppose you have an xi here and a certain function, function of xj only. Then this is 0 because partial x with respect to x is delta, but partial f with respect to p is 0 because f has no dependencies on p, and a similar thing happens here because partial f with respect to x is in general different from 0, but partial x with respect to p is 0. So this is 0. This is a nice property, as you will see in 5 seconds. Okay, let's compute xi vj. This is xi, and bj is here 1 over m pj minus q over mc aj. But if you look at this formula, this is a constant and this is the position x, y, and z. So the dependencies here is xa. So the only term that survives here is the first one with the first one of the second term, because this with this by this property is 0. So this is 1 over m, xi pj is delta ij. So that's it. Poisson bracket xi vj equals delta ij over m. Let's compute now pi vj. Okay, pi. Let's see, bj is 1 over m pj minus q over mc aj. This with this is 0 because of that. So the only term that survives is this. Let's put this minus here, and also the constant q over mc. But this is the same thing that I calculated a few moments ago. This. So this is minus epsilon, and let's see, b is j, c, and a is I, vc. So minus with minus plus q over 2mc epsilon, this is equal to epsilon ijc bc or k or whatever, ijk vk bk. So that's it. We copy here pi vj equals q over 2mc epsilon ijk vk. Now is the turn of this guy, xi p dot j. Okay, the new thing here is this dot, so we can work it out a little bit, because that p dot j equals minus the partial derivative of the Hamiltonian with respect to, in this case, xj. This is true, but it's also true that p dot j can be written as a pj comma h, where h is the Hamiltonian. So let's rewrite this xi comma Poisson bracket pj the Hamiltonian. I guess you're thinking that this makes the complication bigger, but trust me, this is a nice trick, because there is a nice property that you will see in Santi's class called Jacobi identity, which says A, B, C plus A, B, C plus A, B, C equals 0. So in this case we have xi pj h plus xi pj h plus xi pj h. This is Kroneker's delta, but this is a constant because the Poisson bracket is defined by derivatives. Then the derivative of a constant is 0, so this Poisson bracket cancels, and this is good news because our life is a little bit simpler than before. But what is this? This is the same as minus xi h. So let me put here a minus and copy that. But you know that x dot is equal to partial h with respect to OK, but you will see that it's also the Poisson bracket x h, but we call this in this exercise or in general vi. All this Poisson bracket is just vi. Up to here we have that this Poisson bracket minus this bracket is 0. So if we move this term to the right hand side, we will obtain this. So this is equal to this. But you know what it is because it's in here from previous calculations. So this is, let me see, q over 2mc epsilon j I k v k. If you want to put it nicer, ijk, so let's do this by interchanging j and I and putting a minus sign, ajk. So this is minus q over 2mc epsilon I j k b k, and that's it. Let me write this quantity smaller. Great. In order to do this, let's delete a little bit because I have no space here. Okay, let's calculate pi pj dot, and there are many ways to do this calculation, but I've selected the one I like the most. Let's apply the definition, the sum from k partial pi with respect to x k partial p dot j, p k minus pj dot xk pi pk. So we can say that this is 0 because p and x are independent. The whole term, the first whole term cancels out. So great. And this is just Kroneker's delta with the minus. Let's write this in a short way. I define this symbol as a partial derivative to respect xi, and we have here p dot j. Okay, but we know from Hamilton's equations that p dot j equals minus derivative of h with respect to xj. So this is minus plus partial I partial j of the Hamiltonian. Good. But the only thing we know is the Lagrangian, m over 2 b squared plus q over c v dot a. But the Hamiltonian is easy to construct because it's p dot v minus L. We can write p as mb plus q over c a dot v minus L, m over 2 v squared minus q over c v dot a. So this term with this term cancels out with this other term. So mbb is mb squared minus this quantity. So this is just 1 over 2 mv squared. So the Hamiltonian can be written in this way. Of course, we know that v, the vector v, is 1 over m p minus q over mc a. So this is 1 over 2 m 1 over m p minus q over mc a squared. So our Hamiltonian is, if we factor out m squared, 1 over 2m p minus q over c a squared. Or using Einstein's criterion, this is pk, for example, minus q over c a k times the same thing. Remember, vector b squared is b dot b, but this is the sum k from 1 to 3 bk bk. If we forget the summation, like Einstein, this is bk, but instead of v we have all this. So this is the same structure, if you like. The thing is that we have finally the Hamiltonian in terms of the p components, of course. So let's compute partial j of h. So this, only this. So this is 1 over 2m, the derivative of the first term, but the derivative of pk with respect to xj is 0 because p and x are independent. The only term that survives is minus q over c partial j a k. This is the first term, the derivative of the first term, times the second term, plus this term times the derivative of this term. But this is the same thing that appears here. So this is twice. So appears a new 2 that cancels this 2. So here we are. Let's perform, or let's take the partial derivative of partial j h, and let's see, 1 over m. Let me factor out minus q over c, and let's write this here. It's the same because all these quantities here are functions and the functions commute. So minus q over mc times the derivative of this expression with respect to xi, this is 0, minus q over c partial I ak times the second term plus the first term times the derivative of the second term. But what is this? I will show you now that this is 0 because ak equals 1 over 2 epsilon k a b a xb. This is a term linear in x. Xk is something constant, a sum from k equals 1 to 3, but it's a sum of constants times x. Then if you perform a partial j derivative over ak, you will obtain, let's delete, the sum is here. But we cannot see the sum, but it is here. So this is 1/2 epsilon KABA, and this is the derivative of xb with respect to xj is delta bj. So this b is j, and then we delete this. Great. But if you perform the partial derivative with respect to I, this one, this is 0 because all these magnitudes are constant. So it makes us happy because all this cancels out. So let's simplify a little bit. This is minus plus q squared over mc times the partial derivative partial I ak times partial j ak. But we already have these computations because if we delete this, there it is. So partial I partial j h will be q squared over mc. Here we have ik, so this is 1/2 epsilon ki. Instead of j is I, and here 1/2 epsilon k. If you use a repeated index, then you must write another repeated index in the same expression. This is a rule from Einstein's criterion. So this is j and b. 1/2 and 1/2 is 4 here. And let's move this a little bit. So that's it. We obtain that the Poisson bracket we are calculating is this derivative, this double derivative, that is q squared over 4mc epsilon k I epsilon k j v b, and here we have a and b and b. Perfect. There is a nice property that states that this is the same as the second with the second, ab, the third with the third, ag, minus the inverse, ai is the same, but instead of b, j, b. So let's plug in the equation. This will be q squared over 4mc. Let's see. So this times this will be ba delta ij minus bj vi. But this is sum because there is a repeated index. So this is v1 b1 plus b2 plus b3, namely the dot product between b and itself, so b squared. So this is b squared delta ij, and this is, it is what it is, and that's it. The final result is this. So we're finished. See you next week.